Let's take another look at fractions. We saw in our last video that a fraction is defined in two different ways. I can think of it as A being divided by B, or I can think about it as A being multiplied by the reciprocal of B. This relationship is exactly the same as this relationship. When I'm adding, that assumes I'm moving to the right. I'm continuing to move in that direction if there are no signs for either number. If I want to change that direction, I can change my operation to now say A, turn around, go backwards for B. I can turn around and go backwards for B by continuing to use this original operation of addition, but change B to be a different kind of number. I now have numbers that mean go to the left, as opposed to the whole numbers, the positive numbers that mean go to the right. Well, the same is true of dilation versus contraction. If I have A times B, if these are both positive whole numbers, that means I have some number and I'm growing it by some factor, maybe 3 times its original size. But if I want to take that same number and shrink it, I can introduce a new operation that says cut this into 3 equal pieces. Or I can say take this number and multiply it by a shrinking factor, 1 over b, instead of the growing factor of b, right? This is a unit fraction. That's the definition of unit fractions, right? We're shrinking it down by that same factor versus growing it by that same factor. Now, as we get to multiplying and reducing fractions, recognizing that fractions are really multiplication is what underlies all of the rules that you may remember from grade school. So let's look at an example. 6 times 2, that's 6 and another 6, 12. 6 divided by 2, that's 6, cut it into 2 pieces, so that's 3. When I see 6 over 2, I see that 6 cut in half. I'm taking this 6, shrinking it down to half its size, and getting 3. Now, how do I know that that becomes 3? It really has to do with factoring. Right? If we go back to our addition and subtraction again, 87 minus 7 is super easy. I don't have to count 87, 86, 85, 84, 83, 82, 81, 80. You can't see my hand here, I was counting, right? 86, 85, 84, 83, 82, 81, 80. I recognize 87 really means 80 plus 7. So I'm just chopping off that 7. I have addition and subtraction of the same amount, which gives me the identity. So I'm back to that plain 80. Right? That's our shortcut here. The same is true for multiplication. 6 times a half. 6 is not a prime number. 6 is 3 times 2. And so I take half of 2, right? That's the definition of a half, is 2 halves makes a whole. Or half of doubling gets us back to the original. So 3, double it, then halve it, we're right back to 3. We're getting the multiplicative identity. So let's get those definitions down out of the way here. When I talk about reciprocal, that's our single word to refer to the multiplicative inverse. Multiplicative inverse. Just like opposite is the single word for additive inverse. We defined additive inverse already. Additive inverses are pairs of numbers whose sum is the additive identity. So multiplicative inverses are pairs of numbers whose not sum, because we're not adding, whose product is the multiplicative identity. Right? And what is the multiplicative identity, you say? Well, of course, just like the additive identity, the multiplicative identity is the number that when multiplied by another quantity. I forgot this time around, I changed up my sentence structure. The number that has no effect when multiplied by another quantity. Right? Well, that number is 1. We can see this in action if we look at two slightly different problems. So let's say we want to simplify, right, perform all possible operations. 2/3 times 5/7 and 2/3 times 5/6. Okay, we defined a fraction as multiplication. If we see 2/3, we can think of that as 2/3 times 5/7. 5/7. And now we actually have 4 factors when it looked like we only had 2. Well, 2 times 1/3, that's just 2/3. I can't really simplify that. But if I associate my 2 with my 5, 2 times 5 is 10. Perform all possible operations. I know what 2 times 5 is. It's 10. I can perform that operation. Now, 1/3 times 1/7 I might have a harder time dealing with unless I look at a picture. If I take thirds and multiply that by sevenths, I took 1 and I cut it into thirds. Now I'm taking those thirds and cutting them into sevenths. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. Ooh, made that too wide. 1, 2, 3, 4, 5, 6, 7. Not to scale. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So I have 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 15, 16, 17, 18, 19, 20, 21. By cutting something into thirds and sevenths, I've cut it into 21 equal pieces. And there's my answer. 10 21sts I write as a single number. Right? Talk about in the history of fractions, a 21st part was all we had. And so we had 10 21sts. And it was, I don't know historically when it changed for notation, but writing this as a single number so that on the number line, I can look at 21 21sts, 1, cut that out so that I can see all 21 pieces. Here's 10, 11, 12, 13, 14, 15, 16, 17, 18. Here's 21. All right, so pretend those are all equally spaced. Here's 10 of those 21 pieces, as opposed to this one being 1/21st. Right? That's what fractions are. We're dividing by 21 and then multiplying by 10. I took 1, I contracted by a factor of 21, and then I dilated, I expanded by a factor of 10 to get to 10/21. Now I could do the same thing over here. 2/3 is 2 times a third. 5/6 times 5 times 1/6. 2 times 5, I associate those. That gives me 10. By the same logic that gave me 1/21st here, a third of a sixth is an 18th. So I can say 10/18. Take 1, cut that into 18 equal pieces. Maybe go a little bit skinnier. Put a pen here. There's 10. 18/18 is 1. Except that's not going to be marked correct, because simplify means perform all possible operations, and there's a possible operation here that we haven't done. 18 doesn't go evenly into 10. That doesn't mean we can't still simplify. The issue is that 6 is not a prime number, and even more importantly, there is a multiplicative identity lurking within here. We just didn't see it right away. So let's rewrite this. 2, it's a prime number. 3, prime number. 5, prime number. 6, how do I cut a circle into 6 equal pieces? Well, you cut it in half, and then cut it in half this way, and cut it in half that way. Let's fix that. Cut it in half this way. Cut it in half that way. Yeah, that's better. Cut it in half that way. In other words, we take half, and then take this half, cut it into 3. Take this half, cut it into 3. A sixth is half of a third, or a third of a half. Well, I've cut it into thirds and into thirds. If we cut a third into third, you're just cutting it into ninths, right? There's my 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's nothing special about having that same number repeat. It just makes the multiplying easier. What's special is to multiply 2 times a half. If I take 2, cut it in half, I get 1. Or if I take a half and I double it, I get 1. I'm getting the identity. Whatever my other number is, let's say we start with 5. If I double that and get 10, I cut 10 in half, I'm going to get 5. Now, cutting 5 in half to get 2.5, and then doubling that to get 5, that's harder to see, because 5 divided by 2 doesn't work out very nicely, right? That's why the associative property is so useful for fractions. If I can associate the 2 with the 1/2 to get 1, everything else becomes easier. 5 times 1 is 5. 2 times a half is 1. And then 1 times a third times 5 times a third. 1 times 1 times 5 times 1, right? My whole number is just 5. I'm getting 5 times bigger. And then 3 times smaller, and then 3 times smaller than that. So 9 times smaller overall. So 10/18 is the same as 5/9. If I count by 2 at a time here, 2, 2, 2, 2, 2. I have to be really slow to be precise enough here. Now, again, I didn't draw these all exactly the same, but hopefully you can still see. All right, how many of these black circles did it take me to get exactly to 1? 1, 2, 3, 4, 5, 6, 7, 8, 9. And how many black circles did it take to get to my 10/18ths? 1, 2, 3, 4, 5. 5/9 is equivalent to 10/18ths. How do we get from here to here? We recognize that 10 is 5 times 2 and 18 is 9 times 2. I'm doubling and I'm halving. That cancels. Right? So without showing all of this work, how do I deal with 2/3 times 5/6? In real life, how am I going to take care of this? I'm going to say I'm doubling, I'm multiplying by 5, I'm thirding, and then 6, that's 2 and 3. 2 halves makes 1. I don't have to formally show it as 2 times a half. I recognize that when I'm multiplying, 2 over 2 means 2 halves. And that 1, that identity, being multiplied by 5 has no impact. So I have 5 over 3 times 3, 5/9.